Hello and welcome to today's video about the lithium-silicon battery, an advanced battery with a high energy density. This is a comparison of a graphite and a silicon anode. 6 carbon atoms are needed to store one lithium atom. On the other hand, a single silicon atom can store up to 3.75 lithium atoms. Silicon swelling is the big challenge with lithium-silicon batteries. When charging, the battery swells to 3.2 times its volume. This puts stress on the electrode material and causes a quick degradation. For comparison, a graphite electrode only swells by 10% during lithiation. There are several solutions to this problem. Coating reduces the volume expansion, improves conductivity, and can prevent side reactions. The coating can be hard or elastic. It can be based on carbon, polymers, or metal oxides, for example titanium dioxide or aluminum oxide. Coatings must be thick enough to protect the anode, but thin enough to allow ion transport. Composite materials are another solution, for example a composite of graphite and silicon. They combine the benefits of each component and they are designed to optimize mechanical, electrical, and electrochemical properties. There are different types, porous or hybrid composites. Nanomaterials like nanowires with the high available surface area allow a high anode power density and quick charging. Nanowires can take the big volume changes during charging and discharging and provide a better electron transport. One synthesis method is the laser ablation of bulk material, a top-down synthesis. Chemical vapor deposition is a bottom-up synthesis method for nanowires. Silicon-containing gases decompose on a substrate to form nanowires. The cost-effective synthesis of high-quality silicon nanowires at a large scale is a challenge. Further research is needed to understand the mechanical stability of nanowires. The solid electrolyte interface layer SEI is important for the performance and long-term stability of a battery. The SEI is formed from the decomposition of lithium compounds on the anode surface. Its composition is not fully understood. Computer models are used to gain an insight into the surface processes. The growth of the solid electrolyte interface on the silicon surface is an interplay of chemical and mechanical effects. Due to the repeated fracture and healing, the aging behavior is complicated. At high states of charge, mechanical pore expansion accelerates solid electrolyte interface growth. Continuous pore creation during interface expansion deteriorates the inner SEI shell in the long term. This picture shows the electrochemical cycle in a coin cell. During the first charge-discharge cycle, there is an irreversible lithium loss in silicon anodes. It can be measured with synchrotron X-ray Raman scattering XRS. Main solid electrolyte interface layer compounds are lithium carbonate and lithium fluoride. 30% of the carbonates formed during the lithiation are dissolved on delithiation. 70% of the lithium loss in the first cycle is trapped in disconnected silicon particles, while 30% form a fluorine-rich stable SEI. 53% of the lithium is in a carbonate-rich, partially dissolvable interface layer. During lithiation and delithiation, there is a phenomenon of voltage hysteresis, a dependence of the voltage of the system on its history. A core shell model can be applied to the nanoparticle. Only the silicon core is lithiated and delithiated, while the covering shell is chemically inactive. In lithium-ion batteries, there is an excess anode area to prevent lithium plating. The combination of silicon anodes with layered oxide cathodes prevents lithiation of the overhang. This is important for the life estimation of a cell. The binder is an important battery component. Polyimide binders are known for their thermal stability, chemical resistance, and excellent mechanical properties. No coating delamination was found during the first cycle. However, there is a plastic deformation which is dependent on the battery size. The stretching and rippling effect is stronger at bigger electrode dimensions. Future generations of batteries will be far superior to today's batteries. They will make electric vehicles even more efficient. You can check out the links to the scientific articles in the description field. And you can check out my other videos from the chemistry series. Thank you for watching.